Okay, hi. In this experiment, we are going to determine the enthalpy of decomposition of hydrogen peroxide. That means we are going to take some hydrogen peroxide in water. We are going to add a catalyst to allow it to decompose rapidly, and we'll see how much hotter it gets. This should tell us how much heat is released. So the basic idea is that hydrogen peroxide does release heat when it decomposes into the elements, hydrogen and oxygen. We can accelerate that process when we use an iron catalyst. So water, this is the balanced chemical reaction. Water turns into hydrogen and oxygen and heat, and we'll measure how much heat this releases in kilojoules per mole. Here's an example, and this should answer most of the questions you might have throughout this experiment in terms of calculations and understanding it. Imagine you take 8.2 grams of a 3% by mass solution of aqueous hydrogen peroxide. We then add 1.8 grams of the iron nitrate catalyst. Notice that there's 10 grams mass total there. And we combine it in a calorimeter, which is an insulated container. And we raise the temperature from 22.8 to 32.8 degrees Celsius, so it's a 10-degree change in temperature. That's our delta T. What's the enthalpy of decomposition of hydrogen peroxide in kilojoules per mole for this experiment? We need kilojoules per mole. So we need the kilojoules and we need the moles. For the kilojoules, we can use the specific heat equation, Q equals mc delta T. Q is the heat that is released to the surroundings. The m is the mass of the solution. Notice that there are a total of 10 grams from the 8.2 and the 1.8. C is the specific heat, and this system really is largely water, so we'll use the value simply for water. A more precise number might be available, but this is very close, so we'll use the specific heat of liquid water, 4.184 joules per gram degree Celsius. The change in temperature was 10 degrees. There it is there, giving us a total of 418 joules, and a kilojoule, of course, is thousands of joules, so we have 0.418 kilojoules. Now we need to know how many moles of hydrogen peroxide we had. Well, it's 8.2 grams, but it's only of a 3% solution. So 8.2 grams of a 3% solution is really much less than 8.2 grams. And there are 34 grams per mole, and you run that through and we get 7.23 millimoles, or 0.00723 moles of hydrogen peroxide. That's our bottom number for the kilojoules per mole. Punch it in and there it is. This system released 57.8 kilojoules for every mole of hydrogen peroxide. Our general procedure, and as usual I won't list every little step, it's fairly cookbook. Get Logger Pro up and running. There's nothing we need to preheat or anything we can do this time to try to save some time. We'll mass the peroxide into the calorimeter. We'll mass the catalyst of the solution just like they did there. There's the peroxide, there's the catalyst. Start the program, then mix. Don't mix, then start the program. And after 600 seconds, that's 10 minutes, we'll see what happened. You should end up with a curve that looks roughly like this. Note that the final temperature is calculated, not measured, so please follow step 12 carefully. See how things curve off a little bit, and we want to extend that to get a point right there, and that should give us our delta T. Okay. Here's the calculations we'd like to see. There's 6, count them, 6. The final temperature, that's right there, using y equals mx plus b, the equation of a line, so that we can accurately determine where that final temperature is. Notice just drawing a straight line should give you a very good estimate of where it is, but calculating it is the best way to go. The temperature change, which is temperature final, right there, minus temperature initial, which is right there. The heat released in kilojoules and the sample calculation should help a lot there. The enthalpy of decomposition of hydrogen peroxide in kilojoules per mole, and once again the sample calculation gives you the kilojoules, it gives you the moles, and kilojoules per mole is the final answer. A comparison to a theoretical enthalpy of decomposition, and this is something similar to what, at least in this class, we've done last week, where you show the calculation in the appendix for a theoretical calculation, right? where the enthalpy change should be the enthalpy of formation water minus half of the enthalpy formation for oxygen. Hopefully this will bear some resemblance to your experimental value. Some questions to consider that I won't be answering but are worth thinking about. What does the iron nitrate do? Does it affect the energy? Does it affect the timing? Does it affect the stoichiometry? Is it a reactant? Is it a product? These are all things worth considering for this iron catalyst. What's the unknown this time? Is there any unknown? Why is the final negative value negative? Why do we put that negative here, and what does that mean? How do we determine the initial temperature here? How do we do the final temperature using the equation of a line? I hope this helps you understand this experiment, and this is the enthalpy of decomposition of hydrogen peroxide.